Good morning, everyone. I'm Uma Maheshwari, Assistant Professor, Department of Electronics and Communication Engineering. In this particular video, I'm going to explain about Shannon Fano coding in information theory and the error control coding. Here, we'll consider the data. So, we'll be reading about data compaction. In order to transmit a signal efficiently, the redundant information should be removed from the signal prior to the transmission. This operation with no loss of information is referred to as a data compaction or a lossless data compression. The various source coding algorithms for this data compaction are a prefix coding, Shannon Fano coding, Huffman coding, and the Lumpel-Zill coding. We'll be seeing the Shannon Fano coding and the Huffman coding in detail. So in this particular video, I'm going to explain about only the Shannon coding. Here, the Shannon Fano algorithm is one where less number of bits are used for highly probable messages and more number of bits for rare occurrences. The need for this Shannon Fano coding is if the probabilities of occurrence of all the messages are not equally likely, then the average information or entropy is reduced, which in turn reduces the information rate, or it can be solved by coding the message with different number of bits according to their occurrence. The procedure for this Shannon Fano coding is the symbols are first arranged in the descending order of their probabilities. The set of symbols is then divided into two subsets that have the same or almost the same probabilities. All symbols in one subset get assigned codes that start with a 0, while the codes of the symbols in the other subset starts with a 1. Each subset is then recursively divided into two subsets of roughly equal probabilities, and the second bit of all the codes is determined in a similar way. When a subset contains just two symbols, their codes are distinguished by adding one more bit to each. The process continues until no more subsets remain over there. So the example of this Shannon Fano coding is explained with the probabilities with ranging from A1 to A6, that is symbols. We are assigning with a 0 and a 1 probability. So we are equally dividing the probabilities. So in the upper portion we are assuming a 0, in the lower portion we are assigning 1. Then that splitted part is being further divided equally into separate parts. If we have four probabilities, if one is higher, the other three is equal to that one. That will be divided according to the particular code. So then we'll be assigning the code words for that particular code. So from the code words, we'll be finding out the code length. So I'll explain the Huffman coding in detail. These are the various symbols. The probability is 0.25 to 0.5. So we are assigning it in the decreasing order from 0.25 and finally to 0.05. So 0.25 and 0.20, if we add this particular two symbols, we'll be getting 0.45. So if we add from the symbols 3 to 7, we'll be getting 0.51. So this is the equal probability we are splitting. 1 2 is 1 and 3 to 7 is 1. So we are assigning the first part as 1, the remaining as 0. Likewise, we are assuming in equal steps and will be finding a final code word as the code for this particular 0.25 is 11, 0.20 is 10, and for 0.15 is 011. Likewise, we'll be getting these final codes. So the next step is we have to count how many codes are there. So that will be called it as a code word length. So the first step splits the set of 7 symbols into two subsets, one with the two symbols and a total probability of 0.5, and the other with the remaining 5 symbols and a total probability of 0.05. As I said, so we are splitting it like this. Then we are finding out the average. That is, if we multiply the code word length into the probability, and averaging all those symbols and probability will be getting 2.7 bits per symbol. Then method produces a better code when the splits are better. When the two subsets in every split have very close total probabilities. So the two subsets in every split have identical total probabilities which yield the minimum average size, which we call as a zero redundancy. So we will be calculating the entropy. Entropy is nothing but we are taking the logarithm of that particular code word and the symbols, that is probability and the symbol. So we'll be getting 2.508. Then adding this all this will get an average of 2.5 bits per symbol. So the main advantage of this is this method produces the best results when the symbols have probabilities of occurrences that are powers of 2. The Shannon Fano method is easy to implement, but the code it produces is generally not as good as that produced by the Hoffman method. The assessment of this is thank you.